Right, ladies and gentlemen, let's continue with chapter 4 in the textbook of Cengel and Ghajar. We are going to do the last part of this chapter. The first part was lump systems. The second part was large plane walls, long cylinders and spheres. Then paragraph 4.3 was semi-infinite solids. And now the last part is multidimensional systems. Sorry, not 4.2, but 4.4. Okay. But before we now continue with 4.4, I just want to go back to 4.2, which was large plane walls, long cylinders, and spheres. What is very important to remember is that with this part of the work, when we looked at a large plane wall, and that's specifically the reason for the word large, was that it was very long in terms of the thickness of this large plane wall. So in general, there will not be any heat transfer from that surface and that surface. So the heat transfer rate would have been in one dimension, typically like that. And the same for the long cylinder. For the long cylinder, it was typically something like that. And again, the heat transfer rate, maybe in this case, the heat transfer flows out, if only in one dimension. And again, we ignore the heat transfer rate from the top and the bottom. The only exception, of course, is the sphere, which is one-dimensional, and we do not have to specifically refine that one. Paragraph 4.4, we are now going to look at multidimensional bodies, which means that we are not going to look at the large plane wall, which is very long, but it can be a shorter type of geometry, or it can be a short type of long cylinder, which is then called a short cylinder. Now, the approach which is followed in paragraph 4.4 to solve these types of problems is to use something that you've done in mathematics, and that is to make use of the principle of superposition, in which you make use of the product solutions of two different solutions to generate a new solution for another type of geometry. And the example is going to be specifically the case of a large plane wall in this dimension. Okay. Now remember, it is actually, of course, more something like that. Okay. And this thickness we have seen previously was equal to 2L. Okay. So previously, the solution, we always have drawn the large plane wall in this direction. Now it is just going to be in an horizontal plane. And the solution previously was as a function of x, and that is still going to be the case. However, what we're now going to do is we are going to look at the product of the large plane wall and the cylinder. And we are going to do it so that they are perpendicular towards each other. So if we look at that, there's the long cylinder and the large plane wall. And if you use your imagination a little bit, and maybe if you can draw better than I can, you will see the product of it is a short cylinder. And that is shown better in this PowerPoint. So the sketch is much better than mine. Do you see it? So the product of two solutions gives you the answer is that of a short cylinder. So therefore, we can then write that the temperature distribution now becomes a two-dimensional temperature distribution. Previously, the temperature distribution will only be a function of R or X. Now, it is going to be a function of X, R, and previously it was a function of T, minus T infinite divided by Ti minus T infinite, and that would now be the solution for a short cylinder. And that solution for the short cylinder would be the solution, the temperature of xt minus T infinite divided by Ti minus T infinite of the plane wall, okay, the plane wall, in that case, PW plane wall, multiplied by the temperature distribution, which was previously a function of R, and also T, minus T infinite, divided by Ti minus T infinite of the infinite cylinder, the long cylinder. So the product of that two will give us a short cylinder. Now that is not the only type of geometry that we can generate. We can generate other types of geometries also. It is given in your textbook. I can get this thing to move. I don't think you can see it properly, so let me just see if I can make it larger for you. So there are some of the solutions. What is called the infinite cylinder, the semi-infinite cylinder, there's the short cylinder, and there the solution is in terms of non-dimensionalized format. And there are corners that can be, different types of corners that can be generated, and different types of geometries. Okay. Your textbook is not complete, there's more solutions available, but these are some of the important ones that you can take note of. Now, what is actually the secret or the most important thing to remember when you would like to use these types of solutions? It is to go and look very carefully of where the coordinate system has been placed. Where the coordinate system starts from, ends with, is extremely important, because that solution, if they tell you, typically it's the solution for a cylinder, then you need to go and use the equations that has been used previously for a cylinder. And for the cylinder, I hope you remember typically that the diameter is equal to 2 times R0, and for the plane wall, the distance of the plane wall from the left side to the right side, that is not equal to L, it is 2L. Of course, that was used in the derivation. So those are the important things that you need to remember. So let's look at a problem as an example. And this example, I'm going to do different than what I did in previous years. In previous years, I did go and solve all the equations which we have done in paragraph 4.2. I hope you remember them. They are in the table, and they say the sum of n equal 1 to infinite, and then you can look at the first term approach by assuming tau is larger than 0.2. Then you can get the Biot number, and then in the tables you can go and get A1 and lambda 1, and then you have to put it into the equations, and then there's also the Bessel functions the moment there's a cylinder or a sphere. I'm not going to do it like that this year. I'm going to use the solutions from the Heisler charts. Why? Because the mathematics becomes so, it's very challenging firstly to do it in 2 lectures. Normally I take 2 in 1 lecture. Normally I take 2 lectures to do it. And then you do not really follow what is the principle. So really to illustrate the principle, I'm going to use the Heisler charts to get the solution every time. So the example that we are going to do is that of a short brass cylinder. Okay, so that is how it looks like. And you will see in the sketch that that would be X and that would be equal to R. The cylinder is from brass and the diameter is 100 millimeters and it is 120 millimeters in height. The temperature of this cylinder was 120 degrees Celsius, and so it was in an oven. Maybe you're busy with a material treatment or a surface treatment, and then at T equal to 0, the environment temperature changes to 25, so it is taken out of the oven and it is being put somewhere so that it can cool, and the heat transfer coefficient is 60 watts per square meter degree Celsius. And the question that is being asked is to determine the temperature in the center. And I'm going to indicate that as T00. You will see later on why I'm using T00, because there's going to be more than one T0s. So we want to know it in the center, and then we also want to know the temperature there at the top, in the center there, and I'm going to call that T1. Okay, so we want to know what is going to be the temperature at the center and at T1 after 15 minutes. After 15 minutes of cooling. Right, so if we look at this solution, it says the solution for a short cylinder is the solution for a plain wall multiplied by that of the long cylinder. We just put it back like that. Okay. So let's first look at this part of the problem, the plain wall part. So for the plain wall, the solution that we typically have is a plain wall, and now I'm going to draw the plain wall in a horizontal direction. So it is like that, and that is the plain wall, it's very long in that direction, like that. Okay, something like that. So previously when we've looked at the plain wall, that was the center line, and that was equal to 2L. Okay. So in this case, 2L is equal to 120 millimeters, which means that L is equal to 60 millimeters. Now the important thing to remember is that if we think of, we want this temperature at the center, where these two would intersect, we want to know the temperature on that surface there. But we must remember, it is not a line, it is a long surface like that. So that is actually the temperature all the way on that sheet, if I can call it like that. Okay. So if we have previously determined the temperature 0, then it would be the temperature on that line. And it wouldn't represent it actually on the end of it, it will represent it right through the body. Because there's no heat transfer in this direction, all the heat transfer would occur in that direction. It's one-dimensional. So, if you go back to paragraph 4.2, you will see that the thing that we always need is the Biot number and the non-dimensionalized time. Those are the things that we need to either substitute into the equations of getting the non-dimensionalized time as a function of the equations which are given in that table or in the Heisler charts. So the non-dimensionalized time would be equal to alpha t divided by L squared. Okay, sorry, before we get to that, I forgot. Let's first look at the properties of brass. So the properties of brass, you can get that in your tables, and it's in table A3. Table A3, there you can get the properties of brass. And the properties are, the thermal conductivity is 110 watts per meter Kelvin, or degrees Celsius, and the alpha, the thermal diffusivity, is equal to 33.9 multiplied by 10 to the minus 6 square meters per second. Okay. So now we can get to the non-dimensionalized time, which is equal to alpha t divided by L squared. Where do I get that non-dimensionalized time? In the fine print underneath that table. Okay. The non-dimensionalized time for a plane wall is equal to that, and alpha is equal to 3.39 multiplied by 10 to the minus 5. The time is 15 minutes multiplied by 60 to get it into seconds, 900 seconds, divided by L, which is equal to 0.06, 60 millimeters squared. So the non-dimensionalized time is equal to 8.48. The other thing is the Biot number. I'm going to write it as 1 divided by the Biot number is equal to K divided by HL. K is 110. The heat transfer coefficient is equal to 60. L is equal to 0.06. And that would be equal to 30.6. So take note that normally you would go and use the equations to get the non-dimensionalized time as equal to A1 e to the minus lambda blah 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 blah. That's that thing. So that is how you actually should do it. Okay. I'm going to use the Heisler charts because I don't want to put in too much mathematics and make the problem too long. Okay, that's the reason I'm going to use the shortcut. Now, if you go and look typically in figure 14.7 in the Heisler charts, and then you will see why I've written it like that. On those charts, you will get here the non-dimensionalized time at the center, and that is what I'm using this 0 for. This 0 is on that plane. It's a long plane. The non-dimensionalized time on that plane is equal to the temperature at 0 minus T infinite divided by Ti minus T infinite, and on this axis is given the non-dimensionalized time as alpha T divided by L squared, and here lines are given for 1 divided by the Biot number, which is equal to K divided by HL. And now you can see why I solved it as 1 divided by the Biot number. It's because I knew I'm going to use the Heisler charts. So we've got the non-dimensionalized time as 8.48. We need to get the line of 1 divided by the Biot, which is equal to 30.6. There is no such line. Normally the lines would be for 30 and 40, etc. So that's one of the reasons why you will not be able to get a very accurate solution from the Heisler charts. And then it will give you the non-dimensionalized time as 0.8. So the non-dimensionalized temperature is equal to 0.8. And that would also be equal to T0 minus T infinite divided by Ti minus T infinite is equal to 0.8, the non-dimensionalized temperature. Okay. So this solution I'm going to call A, the solution of A. That would represent that solution there. It's the solution of a plane wall. But that temperature is not anywhere on this short cylinder yet, because we are not doing the short cylinder, we are doing a plane wall. Okay, that's the first part of the problem. Let's go to the second part, in which we now consider the cylinder. So for the cylinder, the solution that we can get would be for a cylinder like that, a very long one, and the coordinate system that we've previously used was R, where that is equal to 2 times R0, which is equal to 100 millimeters, which means R0 is 50 millimeters. You agree? Right, now if we go to the Heisler charts again, for the long cylinder, then in principle they are exactly the same. The non-dimensionalized temperature is equal to T0 minus T infinite divided by Ti minus T infinite. Here we've got the non-dimensionalized time, and here we've got the Biot number, or 1 divided by the Biot number. One divided by the Biot number. Okay, so here we've got the Biot number is 30.6, the non-dimensionalized time is 8.48. 8.48, 30.6, and we can get the solution. Do you see that? I hope there's somebody who doesn't see it.
See how that the 30 of the 100 Biot number and the 8
Yes, well done. You'll remember that I said many times you have to look at the fine print when you want to determine the Biot number or the non-dimensionalized time. So for the case of a cylinder, the non-dimensionalized time is equal to alpha t divided by R0 squared. Although alpha t is the same, we now have to use the radius. Okay. And the same with the Biot number. The Biot number is equal to k divided by h and not L, but R0. So they are different. The non-dimensionalized time for the two solutions, although we're talking of the same 900 seconds, would be different, the two non-dimensionalized times. So, if we go and calculate the non-dimensionalized time, is equal to alpha t divided by R0 squared. Alpha is 3.39 multiplied by 10 to the minus 5, multiplied by 900 seconds. The 900 seconds is 15 minutes. Yep.
So isn't alpha supposed to be 33.9?
Yes, 33.9 multiplied by 10 to the minus 6. Okay, okay, multiplied by 900 seconds. Now we have to divide it by the radius squared. 0.05 square, and the result is equal to a non-dimensionalized time of 12.2. One divided by the Biot number is equal to K divided by HR0. K is 110, the heat transfer coefficient is 60, the radius is 50 moles, and that would be 36.7. Right, so coming back to the Heisler chart for a cylinder, that would be, I think, figure 4.18. 4.18. Then we have to look at the non-dimensionalized time of 12.2. That should be 36.7, like that. And from it, we can get the non-dimensionalized time as 0.5. The non-dimensionalized temperature, theta 0 is 0.5. And this is going to be solution B. Okay. Now, if we compare solution A, the plane wall, it would be the temperature in the center, and it would be like a sheet of paper. It is not a line. While in this case, the solution will be along that line. So that is the solution B on that line. If it was a plane wall only. A plane wall only and a cylinder only. Now, let's see if we can make use of the principle of superposition for a short cylinder to generate a solution for the product of the plane wall and the cylinder to get the results for a short cylinder. Okay, so the temperature, if you look at the solution, it would be X, R, and T minus T infinite divided by Ti minus T infinite is equal to the non-dimensionalized temperature for the cylinder, RT multiplied by the plane wall, XT. Okay, so in it, we want to know what is the solution going to be when X is equal to 0 and when R is equal to 0. And that is why I'm going to call that T00. Minus that of the environment temperature is 25. The initial temperature is 120. Minus 25 is equal to the non-dimensionalized temperature for the cylinder multiplied by that of the plane wall, 0.8, and that is equal to 0.4, from which we can calculate that the temperature in the center would be equal to 63 degrees Celsius. You happy with that? Okay. Any questions? Coming back to the second part of the problem. We have asked to determine that temperature, but now we want to determine that temperature there. Okay. So if you look at this plane wall, we want the solution now on this level. So we want to know that solution, which I'm going to call TT at the top. solution at the top. If we look at the case of the plane wall, what do we have to do different? The plane wall case, we do not want the temperature where x is equal to 0, we want to know it where x is equal to L. Okay. So the second part is the center temperature, the center of the top. So we need solution at the TT level for the plane wall. And if you go and look at the Heisler charts for the plane wall, you will see that the charts ask you, say that you can get the temperature at anywhere else, but you must first get the center temperature, and that is then equal to T minus T infinite divided by T 0 minus T infinite. This is as a function of x of L, and this is 1 divided by the Biot number is equal to KHL. In the solutions, the sum of n equal to 1 to infinite, in that there is a place where you do the cos of x divided by L. You're just going to put it in there in terms of the calculation. Okay. So for this case, our x divided by L is, we want to know the solution at 60 millimeters. So that is where x of L is equal to 1. So x of L is equal to 1. 1 divided by the Biot number is still 30.6. And the solution there is going to be 0.98. Therefore means that the temperature divided by the center temperature is equal to the temperature at TT, okay, that plane there, minus T infinite divided by T0 minus T infinite is equal to 0.98. So the non-dimensionalized temperature for the plane wall on the level TT is then equal to the temperature at LT minus T infinite divided by Ti minus T infinite, and that would be equal to the temperature LT minus T infinite divided by T0 minus T infinite multiplied by T0 minus T infinite divided by Ti minus T infinite, and that would be equal to 0.98 multiplied by 0.8, and that is equal to 0.784. Okay, so you can go and calculate that temperature on that level if you want to, but remember that would be the temperature for a plane wall only, okay, at the top. Now, in terms of the superposition, if we want to have the solution for a short cylinder, then we need the solution for the plane wall, but we need it at this level multiplied by that of the cylinder, which we've already done. So in terms of the solution for the top, you can say that the temperature, which is a function of x, r, and t, minus T infinite divided by Ti minus T infinite is equal to the non-dimensionalized temperature. I'm writing out the temperatures like this because I know that you're not used yet to the non-dimensionalized temperatures, but once you've worked through this a few times, you'll see that it is much more convenient to work with the non-dimensionalized values, multiplied by that of the cylinder at 0, and therefore it is equal to 0.684 multiplied by 0.5, which is equal to 0.392. Thus, the temperature where X is equal to L, X is equal to L, R is equal to 0, it's on the center line, T is a function of temperature, minus 25, T infinite, the initial temperature 120 minus 25 is equal to 0.392, and from it we can solve the temperature at point 1. Where's 1 again? Let's just look at the sketch. Point 1 is that one there at the center. You can go and solve it as 62.2 degrees Celsius. Okay? Two more things that's important here. Again, I want to emphasize that I've used the Heisler charts because I don't want to put on too much mathematics and calculations on the board, because it's going to distract you from the principle. You need to understand the principle. Okay? The tests and exams, unfortunately, most probably you will have to do the calculations. You'll see on the Heisler charts, in many cases, the lines are so close to each other, it is impossible to get a very good solution. But the Heisler charts, in many cases, can be used to check your solutions, your calculations. That's the first thing. You will also see that in previous years, I've also calculated the temperature there, at that one there. How would you do that? Well, it would be also the solution for the plane wall at the top, but now, where previously we've looked at the solution where R is equal to 0, you need to get the solution where R is equal to R0. And then you can get the temperature at that point there. Let's call it T2. So we haven't done it here. That's the first thing. The other thing is, I hope you still remember the example of the dead body, where we had to estimate how long ago the person passed away. And for that problem, we have used a long cylinder, which is not the best assumption, because it would mean that all the heat transfer from your head and toes was not taken into consideration. So by using the short cylinder approach, you can include the heat transfer in a second direction. It would be more accurate than the solution that we've done previously for the long cylinder. You've got a question?
Is it a standard thing to times the TLT by T0 to T infinite? So put into that format on the left-hand side, you always just times by T0 minus T infinity.
Let me just see if I can get the question. I know it is about the temperatures and...
If you look at the top formula there...
The top formula, if you refer to the top one, do you mean that one or that one? All right, this one, yes?
Get it into that form.
Yep.
From the right-hand side, you always times by T, you always times by that bit on the right. Because you calculated the T at length at the top of the plane wall.
Yeah.
Using T0 to the bottom there.
Oh, right, okay. So I just want to, okay, let's just go back to the Heisler charts. So the Heisler charts, if you, let me see if I can get one quickly and show you one again. I'm not really sure. No, it's going to take too long now. But in terms of the Heisler charts, the first chart gives you the temperature at the center. Okay? And in most cases, we as engineers are interested in the temperature at the center. The second one will give you the temperature anywhere else after normally you've calculated that value. So from the Heisler chart's point of view, it is always first the best to get it at the center, but then you need to have it as a ratio. What you're now going to solve is as a ratio of the temperature divided by theta 0. Okay. In the equations, it is not necessarily like that. With the equations, just coming back to them, remember the first set of simplifications would typically be where x is equal to 0 and r is equal to 0. And then they've given a set of equations which are all where in the center. Okay. And where the non-dimensionalized time is equal to larger than 0.2. So that's the simplest equations. The next set of equations were when it was not equal to on the center line. Then you need to take into consideration an extra cost term or the Bessel function term. Okay. Any more questions, ladies and gentlemen? Great. If not, thank you very much.